Michael Wolf, PGI Compiler Engineer, back for installment 6 in our series of short videos for your first introduction to parallel programming using OpenACC. In our previous installment, we had optimized the data movement between the host and the GPU using a data construct around the iteration loop of the Jacobi iterative solver. Your homework from the last installment was to improve that performance even more by trying to reduce the dead time between the kernel launches on the GPU. And how we're going to do that is using asynchronous operations between host and device. Here's the same program I had before. There's my data construct. So this is managing the data, which we're pretty happy with. It manages the data traffic between host and GPU as much as possible. And here are my two parallel loops, the matrix vector multiply and the residual computation. What I want to do is decouple the computation on the host and the device, so the host can set up the kernel launches and move ahead to set up the next kernel launch while the device is still busy executing the previous kernel. So I get asynchronous operations between the two. And how I do that is adding an async clause on my compute operations. At the end here, I want to make sure the residual makes it back to the host. So I'm going to have to add a wait construct. This tells the OpenACC runtime, when I get to that wait construct, wait until all the previous asynchronous operations have completed. Let's see how fast this goes. I'm going to build it the same way I did before. Still building for the Pascal GPU. And I'll start with the 1000 by 1000 matrix, which was my default size. Now we're starting to see a little bit better performance. So that seemed to go really fast. But as we know, the whole program here took 1.8 seconds, and most of that is the initialization and finalization of the GPU itself. Let's try running this with a significantly larger matrix size. Let's try a 2000 by 2000, and then we'll try 4K by 4K. So the 2K by 2K, it finished the computation in 1.5 seconds, and the whole program in 1.86 seconds. That's pretty good. The sequential program on the 1K by 1K was taking almost 7 seconds, and we're doing this 4 times as much work, significantly faster. What happens if I double it again? So the 4K by 4K, you can see it takes longer to do that matrix vector multiply. It's an n-squared operation. But the whole thing finishes in less than 6 seconds. So the sequential program, took almost 7 seconds to do a 1K by 1K. Now I'm doing 16 times as much work on the GPU in even still less time. What I want to show, though, is the profile. I want to actually demonstrate the advantage of using asynchronous operations on the GPU. So I'm going back to the profile code. I'm going to start a new profile session. And I'm going to run this with, I'll do the 4000 by 4000 matrix, but I'm only going to do, again, 100 iterations, because that's all we need to demonstrate how much time we're spending. It should not converge, but we ought to be able to see the time out of tolerance. Yeah, 14 is significantly greater than 1,000th. We'll skip ahead to the end here. Here's our timeline. Looks like everything's pretty compressed down here. Let's dive in. Oh, this actually looks quite interesting. I'm going to dive in to try to get one iteration of compute loop. So these enter data constructs, that's where it's checking to see if the data is already present on the device, and we know if the data is present. Here's where it's launching that compute construct. Here's where it's executing the construct it just launched. And then the exit data is at the end of the compute construct, is determining whether it needs to move any data back to the host. Well, in this case, the data is going to stay resident on the device, and so nothing happens. And then there's another enter data. That's for the second compute construct. Here it's launching that second construct. This is enqueuing the upload, so sending the initial value of the residual variable to the device, launching the residual loop kernel, launching the second kernel to do the final reduction, and then downloading the result. So the host here, for this part of the program, this is where it's setting up the computation on the device. And at this point, it's saying, okay, now I need to download the result, and I'm going to wait. So it's done all the setup for all the kernel launches. And where I had this larger gap in the previous profile between the first kernel and the second kernel, now my gap is pretty small because the kernel launches have already been queued up on the device. So this 3 microseconds here, or 4 microseconds, is what it takes for the device to start execution of a second kernel without any interaction from the host code whatsoever. What I get here is a much more efficient use of my device because I'm launching up several kernels and get them all queued up and ready to go. In this particular program, I'm only doing one thing. I'm doing a matrix vector multiply and then the residual computation, which depended on the matrix vector multiply, so I can't get any overlap between those two operations. You could imagine, though, if you had several things that you could do independently, you could launch them on different async queues and then get overlap on the device. You could overlap computation with communication. You can overlap computation with other computation, well, just a little bit, just the tail end of one computation with the startup of the second computation. But nevertheless, you can keep the device busy using asynchronous operations. The question I would ask you now is, what does this do if I run that program where I've added all these data constructs and I've added this asynchronous operation? What does this do if I rerun that program on my multi-core? Did I screw up my multi-core computation by optimizing this for the GPU? That's homework for the user. I expect you to run that to see what the result is, and let us know your results. Thanks so very much for watching this video series on your first introduction to parallel programming with OpenACC.